everybody. Let's understand how vector equations can define linear paths. This is a simple example of a linear path, and we'll understand what it's doing by plugging in specific times, looking at the vectors that it produces, tracing along the tips of the vectors to see what line it creates. But that's not very helpful because we don't ever want to have to make tables again. So at the end of the process, we're going to come back and we're going to ask, what did that part of the equation actually tell us about the end line? What did that part of the equation actually tell us about the line? And then once we've learned those things, we won't have to think about it step by step anymore. We'll be able to think more flexibly about how equations like this produce lines. So let's start. Here I've made a partial table as time goes from 0 to 3. Each time we plug in a t, it's going to become the scale factor on this -1, 2. And remember, whenever you multiply a vector by a number on the outside, that has the effect of stretching or squishing it. So it's going to scale this one vector. So let's go ahead and just fill those parts in here. Okay, I think this is the point at which some groups started to go wrong in class because they really wanted to figure out what are the actual xy components when you add all these things together. And then they were going to plot those points and get the line. And that would definitely work, but I think it's hiding the truth of what's actually happening underneath the hood here. So instead, let's add the vectors graphically, because that's going to show you a lot more clearly what's happening. So one thing I'm noticing is we always have the vector 4, 3 no matter what, because it's not being affected by time, so it's always there. So let's go ahead and add that vector that goes over 4 and up 3. Remember, we're treating these as position vectors, so they'll be starting at the origin. So there's our 4, 3. Okay, when time is 0, this other vector is getting scaled down to length 0, so there is no other vector to add. So at time 0, we start there. What happens at time 1? Remember that when you add vectors, it's as if you're doing one displacement followed by another displacement. So let's look at those two vectors separately and then imagine the result that you'd get if you did one and then the other. So here I do the 4, 3 displacement, and then here I'm going to go left 1, up 2. So I'll sketch that much. So here is the end point, and if I wanted to sketch what the vector sum was, it would be this vector that points to that same end point. But that's where I'm going to end up at t equals 1. Okay, let's do another one. What if t equals 2? So you could think about it this two ways. I could do the 4, 3 displacement, and then you could think about this as doing 2 of the -1, 2 displacements. So I could do a -1, 2, and then I could do another -1, 2 like this, ending me here. A different way to think about it is, let's take this vector that's -1, 2, and let's stretch it to be twice as long. So instead of -1, 2, now it's -2, 4. It's twice as long, but in the same direction. Either way, if you imagine doing one displacement and then the other, you'll see you got the 4, 3, and then we've got the scaled 1, 2, which takes us to here. Hopefully you're starting to see the picture. We've got time 0, 1, 2. What about time 3? For time 3, I'll do the 4, 3 vector, and then I'll do 3 times the -1, 2, which takes me to here. Where do you think I'd be at time -1? At time -1, I'd do the 4, 3 displacement, but then I would scale -1, 2 by -1. And remember, that just takes that -1, 2 vector and it flips it around the other direction. So it would be pointed there. So here's where I'd be at -1. At time -2, I would be taking that vector here, and I'd be flipping it around because it's negative, but I'd scale it to be twice as long. So instead of right 1 down 2, I'd go right 2 down 4 to here. So that would be time -2. So what you see is that the 4, 3 vector takes us to a particular place, and then adding different scalings of this vector is going to take us in the direction that the vector points. The original vector is pointing at -1, 2, so it points this way. And as I scale it positively, it gets longer and longer in that direction. And if I scale it negatively, it gets longer and longer in the other direction. But no matter how I scale it, it's always going to take me to a point that lies along that line. So let's go back to the original equation. A lot of groups called this 4, 3 vector the starting place because it's not being affected by time. It's always there. It's where you start. And we could call this vector the direction that you move in. So you could think about it as, let's choose some point to start at, and then we'll have a vector that points in some direction we want to move in. And if we scale it by time, that means that we'll just continue to move in that direction as we scale it more positively, or in the opposite direction as we scale it negatively. And those two things added together are what create the line. If that's how you're thinking about it, we could have created this line in a lot of ways. Here's my best sketch of that same line up here, only without scaling. So originally we started at a point 4, 3, but if I wanted to, I could choose any point along the line as my starting point. I could choose a point way down here, and that could be my initial vector. And then I could time scale another vector that could be a very long vector, but as long as it points in the direction that the line is going, it's still going to produce the same line. So that's a useful general idea. You can start at any point on the line, and you can move along a vector, and any vector will work so long as it points in the direction you want to go. So let's do a specific example of that. Here I started at 4, 3. What if instead I started here? This is at 3, 5. So I could say, let's start at 3, 5, and let's add a time-scaled vector that is twice as long. So instead of -1, 2, I'll have -2, 4. This new vector equation, you'll notice it doesn't have the same vectors as the original one, but it traces the exact same line. The only difference is now we're starting at this location, so this is the new t equals 0. And then for each second that time goes up, I'm traveling twice as far as I originally did. Because before, every additional second, I just went over 1 up 2. And then another second passes and I go over 1 up 2. Here, a second passes and I go over 2 up 4, over 2 up 4. So each second I'm going twice as far. If you wanted to, you could also think about it this way. Let's factor 2 out of here. And now I've got -1, 2. So you can see, as time passes, I'm still traveling along my original vector, only now I'm doing 2 of them for each second that time passes. So these are the same equation. They're saying the same thing. And hopefully you're seeing now how you can flexibly make whatever line you want. Come back in the next video and we'll do a couple practice problems where you think about making any sort of line you want.